Hello, I'm Etienne Bosset, and I'm head of platform at Secretarium. Today, I would like to introduce how to achieve zero trust with confidential computing and WebAssembly. The zero trust threat model assumes that the attacker is already in the network, but we can push that a little bit further. The attacker also has root access to your server. In that case, the main goal will be to reduce the impact of an attack. We need to time-bound the attack, we need to isolate the workload, but also we need to reduce to its bare minimum what we call the trusting computing base. We can split a zero trust architecture in two main parts. The first part is all about access control, authentication, authorization, but also workload isolation. Those three parts are rooted in one concept, identities. We need tamper-proof and cryptographically verifiable identities for devices, services, and users to make that happen. And then from there, we can derive encryption in transit, authentication, authorization, you name it. The second part is all about runtime protection. An attacker with root access on your server can still spy or tamper with your data and your code. Here it's all about keeping the integrity of your code and data while in use. To bootstrap a zero trust architecture, we need workload isolation, strong identities, and runtime encryption. Confidential computing plays a pivotal role into that. We all know that trusted execution environment provide a hardware isolation layer with runtime encryption, protecting code and data while in use. But it also provides strong identities, guaranteeing the integrity of data and code in a verifiable manner with local and remote attestation. However, if we want to add a state and protect data at rest, another technology is needed. And here, distributed ledger technology is really suitable. They are tamper-proof, immutable, and provide strong auditability. And finally, to host guest application within enclaves, WebAssembly seems the perfect fit with its portable and compact form factor. It provides robust memory sandboxing to bootstrap isolated execution context, and it enables the deployment of untrusted code in a secure manner. And there you have it, runtime protection, strong identities, and isolated workloads. And from there, just a few steps are missing to bootstrap a zero trust architecture. And that's what the product I'm working on, Clave, is doing. It reduces the trusting computing base to its bare minimum. It's your WASM apps in a secure hardware enclave with no hypervisor involved. It implements a zero trust runtime using trusted execution environments where sensitive data remains encrypted and isolated in transit, in use, and at rest. It leverages certificates, cryptography to continuously verify the identities of the platform components, apps, and devices. And finally, it offers a global platform with scalability and resilience built in. But that's not it. We have to make that available to all developers. But let's deep dive in a quick demo. Let's get into it. So first, I'm going to scaffold the WASM application that we're going to deploy in a trusted execution environment. For that, I'm using the Clave tooling. So yarn create enclave. I'm going to call the application mycc demo. I'm just replying to all of this question quickly. It's picking up my configuration on my laptop automatically. And then I'm going to go into the folder that has been created. It's called mycc demo. I'm going to clear that so you can see. And I'm going to opening my IDE, and here it will be code, Visual Code. So here there is two methods here. We are developing in assembly script. It could have been in Rust or any language that compiles to WASM, to WASM in the end. But here it's WASM assembly script. I'm going to add a new method, which is just a ping query to say hello world from the keys and from the WASM app. I'm happy with that. So let's commit. So git add, git commit, initial commit, that's fine. And now I'm going to go on Clave and deploy that. So I'm going to go on Clave, login. That's it. Deploy now. Okay, it's picked up automatically from my remote GitHub repository. It's deploying. So what has been happening here is that it compiles the app into WASM and deploy it on a cluster of 3 different trusted execution environments. So there we go. We can play with the application. So I'm going to do the ping that we've deployed. Hello from the WASM app within the TEs. Okay, all good. This application that has been deployed has a strong identity. Identity comes with the hash of the app. We have deterministic builds, but you can verify that the hash is always the correct one. But also, they also have a cryptographic identities from where we will derive the encryption in transit, but also authentication and authorization. And on top of that, as they are deployed within enclaves, they inherit as well the enclave's identity. So I just did an IntelliGX attestation here. So it tells me that it's deployed on a cluster of trusted execution environments that are running on machine with the latest microcode, but also that it's running within a specific enclave. This is the signature of the enclave here, which corresponds to a specific code that you can also build yourself and verify, as it's open source. The Emer signer is the signer of the enclave, which is our company, Secretarium. It will always be the same here. And then you have a contract digest here to verify that the attestation against which application you're doing is the correct hash. So there you go, you have it. You just deployed a WASM application within an isolated context on a cluster of trusted execution environment with strong identities for the app and for the enclave that leverage, by the way, local attestation and remote attestation to attest themselves. And now the last step is just making sure that you implement a good authorization and authentication system for your users. But that's a story for another time. Thank you very much for your time.